Hello, and welcome to today's HCI webcast, Quality Attribute Concerns for Using Microservices at the Edge. My name is Shane McGraw, Outreach Team Lead at the HCI, and I'd like to thank you for attending. We want to make our discussion today as interactive as possible, so we will address questions throughout today's talk, and you can submit those questions in the YouTube chat area, and we will get to as many as we can. Our featured speakers today are Mark Nowakowski and Grace Lewis. Mark is a senior engineer at the HCI, where he currently is part of the Tactical and AI-Enabled Systems Initiative. He has more than 20 years of professional software development experience spanning defense, commercial, and academic fields. Welcome, Mark.
Thanks for having me.
Grace Lewis is a principal researcher also here at the HCI, and she leads the Tactical and AI-Enabled System Initiative. She's a principal investigator for the Characterizing and Detecting Mismatch in ML-Enabled Systems Research Project. Good afternoon, Grace. Now I'm going to turn it all over to you. Grace, all yours.
Thank you very much, Shane. Welcome, everybody. It is my pleasure to be introducing and also moderating this session for my colleague and friend, Mark Nowakowski. I think you're going to enjoy this session a lot because he's going to be talking about the challenges at the edge that not all of us get to experience as developers. As he's talking about those challenges, he's going to talk about architecture decisions that he had to make when implementing a system or several systems at the tactical edge. If you have any questions, we want this session to be interactive. Please type them in the chat. I will be passing those questions on to Mark, time permitting. And we hope to have a really, really great session. So with that, Mark, all yours.
Thanks so much, Grace. Looking forward to it. So hello and welcome. Again, my name is Mark Nowakowski, and I'll be talking to you today about the architectural issues associated with using microservices in edge environments. Our hope is that you'll come away with a better understanding of the challenges of edge environments, architectural solutions to those challenges, and some insight on why microservices can work well in these environments. We'll be sure to take time for some questions, so please don't hesitate to type them into the chat, and we'll handle them as time allows. So let's get going. So this is just our legal page. It's probably visible before everything started. If you have any questions, feel free to reach out. Otherwise, let's move on. So what is this talk going to be about? Well, we'll start with an overview of who we are and the kind of work that we've done, including a brief discussion about why we feel the space of computation in edge environments is important to work in. Next, we'll talk about the unique challenges of edge environments, differentiating between military tactical edge environments and humanitarian edge environments, which are often part of the equation for first responders during recovery operations for natural disasters. Then we'll explore how these challenges manifest in both types of edge environments through the use of quality attribute scenarios, culminating in a combined scenario that provides context for how and why these challenges might be found in edge environments. Finally, we will discuss how microservices can be a powerful tool for addressing the challenges we've discussed. I also want to take a moment here and just address the fact that this particular webinar is going to be given at a relatively abstract level for those of you who are familiar with our normal HCI offerings. While we typically like to ground our technical offerings in concrete examples that can be examined and dissected in detail, this particular case, the sensitivity of the work that we have done in this space precludes that approach. So instead, the intent of this webinar is to provide a broad brush of the challenges that we've directly encountered with our insight on how to solve them without going into too much specific details on our specific experiences. The edge space is sufficiently rich enough to make some subset of these challenges relevant to any individual project. And our hope is that the insight we share will provide useful direction in how to overcome the specific challenges that arise. With that said, I will, of course, answer any questions as best I can to provide additional insight. Just to check in with Grace, any overview questions about what we're doing so far?
No, Mark, we're good.
All righty. So let's get started then. Okay, so just as a purpose of introduction, let's talk a little bit about myself and my team. I myself work for the Tactical and AI-Enabled Systems Initiative here at the HCI under Grace, and we're a team of researchers, engineers, and other technical experts who have been working in this space for about 10 years now. While our focus has shifted over the years, applicability at the tactical edge continues to be a primary theme, and you can see that we focus on a variety of applications, including networking, machine learning, back-end and edge infrastructures, as well as security. In general, we try to cover all the issues you may find at the Edge. Anyone who's interested in more information on Taz work can drop a question in the chat, who, like I said, is our fearless leader. As for myself, I've been with SCI for over 11 years now, and before that was working with Raytheon for over 8 years, and I've primarily been working in the tactical space using a variety of technologies, most recently focusing on microservices. I've done work for pretty much all of the services, which has informed the content being presented here today. Pausing for questions. All righty. Moving on. All right, so now we actually get to the topic of the webinar. What are we going to talk about today? Well, I'd hazard to say that as an industry, we're pretty good at building complex systems as long as they reside in safe locations and do relatively predictable things. One of the main challenges we face in the world that we have today is scaling operations up, primarily along the vectors of data and capacity. What I mean by that is, in general, when we try to improve machine learning algorithms or provide more capability to our searches, we're effectively adding and processing more data to create a better result. Similarly, when we're trying to increase the number of users that a service can handle, we're scaling up our capacity of our services. There are, of course, different solutions to implement the specific type of scaling that we need for any particular situation, but the key is to scale up. We're all pretty familiar with what that means. Unfortunately, scaling up is not the key problem you face when you build services to run in edge environments. Here, you have to worry about processing, executing in unsafe locations, and furthermore, handle dynamic situations that can change unexpectedly. We're not good at solving those problems. Our solutions in the commercial and government world has always been to build better networks to access bigger systems that allow us to scale up. While those efforts will continue and are continuing today in several engagements that we do and participate in that Taz is part of, we must design and architect our systems to operate in the edge environments given these challenges. So the question becomes, how do we do that? And my answer, based on our experiences in these environments, is to build systems with an eye to scaling down, not up. So what do I mean by that? I mean that if you have a computational capability in an edge environment, it should be architected to be resilient to losing resources. Now, those resources might be connectivity, they might be computation, they might be storage, or even just power. And the challenges you face will be specific to your application. But in general, the goal is to maintain operations regardless of the loss of resources. And you can express that as the concept of scaling down, specifically scaling down operations to the resources that you have, because you know that whatever you start with will probably not be what you have at the end of the day. And as you can guess, microservices are a key component of that. Okay, any questions there?
We're good, Mark.
Okay, moving on. All right, so let's talk about the edge and the challenges that are operating there. So what is the edge? Let's begin by making a distinction between the tactical edge, the common name for the last mile where military personnel operate in the field, and the humanitarian edge, which is a term that I've kind of created that isn't necessarily specific, but just what I'm using to describe the similarly disadvantaged environment where first responders and other emergency personnel might operate. Now, there very well may be better names, and I'm not certainly going to put a stamp on this. I'm just trying to set the context here. And really what we're talking about is all of the different situations in which computational resources are limited, which can include weather events, there could be seismic events, or even infrastructure failures. So, it serves to set the context. So, given these situations, personnel are generally working within limited computational resources in unsafe environments in which things can change at a moment's notice. Another earthquake might hit, or something might fall because of damage that was already done because of the hurricane, or something like that. And you can see that in a variety of ways, as documented in the callouts in the diagram on the slide. First and foremost, a big issue here, obviously, is that the local network infrastructure will often be down or limited, making your cloud resources, which we all rely upon, unavailable or unreliable. The compute that is available, typically handheld or vehicle mounted, will then be limited by available power, which could also be a critical issue if fuel or other power resources are also unavailable. Then there's the context of the crisis, especially in natural disasters. First responders go in without knowledge of the actual situation on the ground. That means there is a discovery and triage process that requires constant shifting of resources in order to prioritize issues as they occur, especially when the need is medical, for example. As a result, first responders must rely upon the resources that they carry into the situation, with only a loose plan of prioritizations as issues are identified. Furthermore, these first responders are typically under-equipped for the jobs they are tasked with and rely upon having resources sent in over time or as the situation allows. Think Haiti, for example. Therefore, the humanitarian edge is a challenging environment of maximizing available resources, computational and other, on an unknown timeline for potentially unknown issues and being able to continue operations in these environments regardless of resource exhaustion, or the individual challenges of the cause of the disaster. It's a critical challenge that the software industry must work to address in order to support these engagements. Okay. All right. So let's talk next about what is typically referred to as the tactical edge. What is the field environment where military personnel execute missions. Think, boots on the ground. That's what we're talking about here. This can be a variety of environments from air to ground to undersea and can range from urban to rural settings. The image here, the picture that we came up with, just kind of shows a canonical example from the last 20 years of American military operations, a desert rural environment in which a variety of different types of military groups are present and performing actions. In these environments, warfighters are trained to bring whatever they need with them in order to ensure that the resources they need are available to perform their mission. As a result, while there may be some local infrastructure and/or resources, they are typically ignored in favor of military assets. However, the trade-off is that military resources tend to be limited at the tactical edge, from the power to compute to connectivity, and dealing with disconnected, intermittent, and low bandwidth, or what's commonly known as DIL network environments, is an expected part of tactical edge operations. So while resources and limitations are known, the risk is always that the nature of tactical missions will result in resource needs that aren't already provisioned, resulting in a disadvantage. Of course, we need to acknowledge that our great military, this is the role of training and planning that they do. Warfighters train relentlessly to adapt to changing circumstances, and careful planning typically will provision them with the best tools available for the mission at hand. Unfortunately, because of the rigors of the tactical edge environment, those tools tend to be simple, purpose-built equipment, which are generally not adaptable to the changing needs of the warfighter, necessitating a large loadout of equipment to handle all of the possible threats. It is this adaptability gap that our work seeks to address and explore, and this webinar seeks to encourage and assist our viewers in their explorations of this space to make the equipment that our warfighters use more adaptable to their needs. Okay. All right, moving on. All right, so having discussed both types of edge environments, we can categorize the challenges into 4 primary concerns, which I've broken down into network, power, compute, and conditions. The challenges for each type of edge environment are different for each category, and this table will give you kind of a good overview of what we've discussed of the last 2 slides. Because we discussed the last 2 slides and gave a bunch of examples, I'm not going to belabor the content here, but I will say that no edge environment is exactly the same, and the list will have to be reevaluated for each one. However, the table provides a good starting point for any system that needs to be able to operate in an edge environment. And the design can then focus on the subset of challenges that a particular mission faces. With that said, I should acknowledge that mission-specific optimization is much more likely on the tactical side. The planning cycle is certainly much more able to anticipate mission needs, whereas humanitarian missions are often unanticipated, and you will tend to have to go in with whatever you can based on based on what you know. In both cases, therefore, a general adaptability capability is important in order to handle the uncertainty, as we will discuss in the next section. Okay. All right, move on to the next section. No questions so far? All right. So let's start discussing how these challenges manifest architecturally in systems that are designed to operate at the humanitarian or tactical edge. And we're going to start by exploring system architectures by building quality attribute scenarios, which is an SEI architectural construct, and build them around typical mission needs. To do that, we need to set up some assumptions about what the scenarios will entail. As this slide discusses, we're starting by assuming that the person that is at the edge, whether it's tactical or humanitarian, will have some low level of capability via a mobile device and with some limited connectivity and some level of limited power source, which is often just going to be their battery. With respect to the context, we can assume that the mission is dynamic and can change, so that the person does not have a full understanding of the situation, or in other words, they have limited situational awareness, and there's going to be some level of danger. We don't know what it is, but there's going to be that uncertainty and this potential danger. So that person might be a part of a small group or entirely alone, and some portion of their attention will be dedicated to avoiding personal injury or equipment damage. Essentially, we're basically considering missions that are dangerous and that feature limited compute, network, power, personnel, and attention. So given that context, we can now consider the quality attributes that are relevant to missions of this type. Okay. All right, moving on. All right, so here's just a basic list of what our experience suggests are the most relevant quality attributes to edge environments, both kinds. I want to take a moment again and acknowledge that we're just throwing a list of quality attributes at you here without any specific architecture or experiences to ground that list. But, like I said, we can't go into detail about that in this venue. So what I can say is that our experience suggests that these are the most important 7. They are the key quality attributes to look at when designing for the edge. I will, of course, define what I mean for each so we can have that grounding. And I'm also able to provide a quality attribute scenario on demand that drives need. Please let us know if you want those technical details. Of course, if you'd like to discuss any of these in more detail, you can put those questions in the chat. And if there's, for example, a quality attribute that doesn't appear in the list that you may think is relevant, feel free to ask. Okay.
Mark, I do have a question for you.
Yes.
So one of the challenges that you mentioned was about conditions, right? And about how people that are operating at the tactical edge are under high, I would say, pressure and things like that. The quality attributes that you have here, it seems like none of them hint towards kind of like an HCI perspective. Is that something that you consider as well? Meaning that there is some component of human-computer interaction techniques or quality attributes that would have to be dealt with just so people can focus on what they should focus?
So I think that's a great question. I think that with every system, the interface is going to be an important part of that. Our experience, what I will say is our experience seems to show that especially in the tactical edge scenario, training tends to get the warfighters accustomed to whatever they're given, even if it's clunky and poorly built. And they're much more concerned about the automatic capability of the system being able to support them while they're doing other things. So if they have to shoot at somebody, if they have to start dodging bullets, if you're worried about the building that earthquake made unstable, it's about to fall on you, then you want to focus on that task at hand. And having a heads-up display, having a intuitive UI is always going to be helpful, but it becomes it tends to be less important in our experience than the sensing of the situation and the reacting to the situation.
Thank you, Mark. There's another question from the audience. Somebody's curious why autonomy is not on that list.
It is. It's the 3rd one.
Fair enough.
Anything else?
Or maybe, actually, Mark, I may have interpreted the question incorrectly. The question might mean, what do you mean by autonomy? Perhaps that is the proper question. It just says autonomy question mark.
And I will definitely answer that question. What I'm going to then do is go through each of these in detail, talk about what I mean, how we define them, some examples of how they come into play, and things that we can do architecturally to support those. So I will answer that question in about 3 slides.
Sounds good. Thank you, Mark.
Cool. All right, moving on. All right, so let's start with reliability. for our purposes, we've defined reliability to be, as much as possible, a system at the edge must be able to perform in adverse conditions and environments. We define it to mean that the system is able to operate at the edge with minimum possible degradation from an ideal environment. So what do we actually mean by those words? Because they're, they could be interpreted in slightly different ways. So a little bit more clarification is that the difference in performance between your capability at the edge and your capability in a safe, non-challenging environment, such as your office or a military base, that difference of capability when you're operating in those two places is as small as possible. And that possible gives you a wide range, right? So given the challenge of the edge, it isn't saying that you are expected to be able to overcome all the challenges all the time in order to be reliable, just that you can adapt to known challenges as well as is reasonable. So if you look at the diagram, you have two groups of soldiers at the tactical edge who are trying to communicate wirelessly, and in this case are being jammed by a third party. Really simple, easy reliability scenario. In practice, you may or may not be able to overcome the jam. And there's a range of outcomes, such as you might have reduced bandwidth or intermittent connections. A reliable system, therefore, would be architected to adapt as well as possible to known jamming attacks in this case. And then you can kind of extrapolate that to other edge challenges. To provide some potential architectural insight, some architectural tactics that you might use to build for this sort of scenario includes, of course, modularity and monitoring via feedback loops. You often want to be able to switch between connection types to adapt to the environment, should your wireless devices allow it, and building your network interface layer to be modular so you can swap in and out the different interface implementations. That will allow the person operating the device to manually or even let the device automatically switch between interfaces to find the best one at the current time. Similarly, in order to make those decisions, you will often have to monitor your performance in the environment, either by looking directly, in this case, at RF emissions, or indirectly monitoring your capability against your performance against some level of known performance in a well-connected state. And then let the user know that they, or the system itself, can detect degraded or disconnected conditions and then allow them to cycle through the other connectivity options. Of course, while connectivity is the primary motivator for focusing on reliability, there are also non-network related reliability issues, such as environmental hazards that degrade operational capability. A great example of this would be the robots that are used to work on the Fukushima disaster in Japan after the tsunami hit. And those robots need to be built both in hardware and software to maximize their reliability given the environment that they're working in. There's an expectation that they will degrade due to the radiation in the environment. And we've seen that models that use feedback loops to monitor the environment and move safely through it is really the only way to maintain operations in these challenging environments. Some of you may have seen the show Chernobyl that has very similar type things, a very similar type story. And so you can imagine that, if you're in these hazardous environments, paying attention to what's going on, whether it's an environmental challenge, whether it's an opposing force challenge, whether it's just a challenge of failure of your devices, you need to be able to monitor and adapt, and that's what we're trying to get to with respect to reliability. Okay. All right. Moving on. So let's talk next about survivability. In this case, what we've defined survivability to be is, given the edge challenges, a system must be able to survive them physically. Survivability therefore means that the system will continue to operate despite damage to the hardware, which could be compute, power, networking, or even the user. So what we are talking about here is the survivability, of course, is related to the reliability challenge that we just talked about, especially when you start talking about robots being degraded by radiation. However, the key distinction that we're making is that reliability is about a system adapting to a challenging environment to maintain capability, while survivability really gets to an acceptance of physical resource loss and maintaining capability regardless. This is really the first instance of a quality attribute where the notion of scaling down really comes into play. Given a physical loss of compute power networking, the system should adapt and maintain as much capability as possible, ideally prioritizing capabilities in order to triage based on the current needs of the user. A survivable system will therefore continue to operate when it is damaged, as long as it possibly can, giving the user every last resources that it can, as long as it can. And we've represented this idea in the slide with a warfighter being in cover with damaged and destroyed devices. In these cases, survivability of the devices to be able to continue to operate and provide services to the users, it becomes a life-critical issue for the user. And so it becomes incumbent upon us as the software community to ensure that they have whatever support we can provide for these situations. So again, to kind of ground it in some of the architectural tactics that you can use to try to address this, of course, we're talking again about monitoring via feedback loops as the key approach to the problem, as well as configurability to allow user prioritization, as well as platform orchestration in order to most effectively use available hardware. And that will, of course, be primarily best served by taking a modular approach. While this again sounds similar to the tactics used for reliability, the key difference is the monitoring is focused on the internal state of the computational device, while reliability is more focused on the external environment via sensors. Though, of course, it also makes perfect sense to hook the two together so that the survivability monitoring is aware when there is a danger of an environment-based resource loss due to reliability-based sensor monitoring. I should also note that backup and redundant hardware is clearly a precondition for triaging capability appropriately. But from a software architecture standpoint, which is what we're concerned at, the system will need to be able to orchestrate the system to actively assign hardware resources using the redundant hardware that's available. Okay. Okay, moving on. All right, so let's get to the question. So the third key quality attribute we've identified is autonomy. Now, autonomy means many things, of course, and so it is especially important to define it here. In this case, the definition that we're using is probably not as detailed as a lot of the definitions that are out there at this moment in time. We're basically just saying that autonomy is where a system at the edge must have some level of intelligence. We're not defining that level of intelligence, but some level of intelligence in order to operate while the user is distracted by mission or environmental concerns. Autonomy, therefore, means that the system can perform some variable set of actions on its own without user intervention. So the need for autonomy is therefore based on the challenge of edge environments being dangerous and requiring significant attention. A common term that many of you may have heard for this is cognitive load. In both humanitarian and tactical edge environments, users will be focused on their job and their surroundings. That means their devices cannot demand their attention unless it is critically necessary and should at least have some limited level of autonomy to assist without interaction. There are, of course, a slew of different autonomous behaviors that can be employed. And our goal here is not to suggest specific ones. That's not what we're trying to do, but just that you need to tailor the type of edge environment, use that to tailor the computational devices that you bring into this environment. In the example diagram, we have EMT providing medical assistance while their device automatically communicates and potentially coordinates with other units, which could include a variety of behaviors contributing to the automation. Some examples include voice recognition or voice commands, video processing to identify the type of intervention being used, or processing of data with wireless biomedical sensors to provide additional guidance and insight, all while the user focuses on the task at hand. Architectural tactics for enabling this kind of capability include monitoring feedback loops, state management, rules engines, and other programmable logic. Of course, autonomy is an especially large topic in the age of artificial intelligence, machine learning. So let's be clear that we're not concerned with a specific type, but tailoring an appropriate type of autonomy to the needs of the user in the edge environment. So it can range, of course, from complex machine learning used by robots. Here, a great example is the snake robots that were developed by CMU that were used to search for fallen buildings, for survivors after the 2017 Mexico City earthquake. And on the tactical side, there are the big dog robots developed by Boston Dynamics to support warfighters. And then you could also go to the edge of, it can also be autonomous agents available on mobile devices in the mold of Siri or Alexa or the Google Assistant, purpose-built to support tasks in the edge environment. So there's a wide range, and the level of complexity can differ. It just needs to be tailored to the challenges of the environment that is going.
Mark, I have several questions that I would like to ask you now.
Sure.
I'm glad you answered the questions about autonomy, because there were several questions related to basically why is autonomy a quality attribute? But I think you did a very good job of explaining what exactly you mean by autonomy, which once again is always the question about, when somebody says I want a system to be X, you really need to define what that is. So I'm glad you did that.
Mm-hmm.
There are two questions I want to ask you. The first one, I was going to wait until you talked about distributability, but I'm going to ask it now because I think it might be more related to autonomy. So somebody asked, should accessibility be included in this list, or does distributability meet that requirement?
Accessibility. That's an interesting question. Potentially. It really, as you stated, Grace, it really comes down to what you mean by accessibility. Mm-hmm. So accessibility to me is something along the lines of ease of use and ability for arbitrary people to use. And that's really not a concern for the tactical edge, right? So warfighters have their systems, their provided provisions, they provision those systems, and everything's all set up. The question is, what can those devices adapt? With respect to the humanitarian edge, I think that's a good question, especially because whoever's in the environment, it would be great if they could help, and it's great if they could have tools to do so.
Right, and you also have a lot of volunteers, right, that come up in that. Yeah.
Absolutely. And certainly, if they can just download an app from somewhere and be part of that solution. I'm thinking of the Bluetooth peer-to-peer app that happened after the flooding down in the South. Those sorts of situations really allow a community to come by. And I can definitely see that as part of that. But I will say that accessibility in terms of enabling operation in edge environments, it really comes down to whether the infrastructure is in place and whether the UI supports that or not. And so that is something that we know how to solve. So while I do agree that it is important, I think that we have solutions that are out there that do a pretty good job at it. I would love to have a scenario to kind of pick through to discuss whether that becomes more challenging for a particular disaster environment, for example. But yeah, I think that while I agree that there's definitely space in there, I'm going to say that it's probably not as big of an issue because it really only comes up in one of the two environments.
Okay. Actually, we had a clarification on what is meant by accessibility, so thank you very much. Accessibility is defined as the ability to access other systems that make up the requisite ecosystem.
Okay. To make up other systems. Okay. I feel like that is a networking challenge that is in a different bucket. And so it's really if you can solve the connectivity issue, which becomes more of a reliability issue, then either you have permissions or not. It really, again, it comes down to whether we're in a disaster scenario or whether you're in a tactical edge scenario, because in the tactical edge scenario is very much an authentication authorization challenge, right? Either you have the ability to connect or not, and really it's just whether the connectivity is there. In the disaster scenario, especially when trying to get citizens and the communities to work together, it is certainly an issue to make sure you can access those things. But again, it really comes down to having a resilient infrastructure to provide that connectivity.
You have other questions, but I want you to keep on going because I'd love for you to get to the microservices part. I'll keep these questions in the queue.
You got it. All right. So next up, we have adaptability. So the definition that we're using here is that things can change at the end moment to moment, and that moment to moment is really important. Adaptability means that the system is able to change what it's doing at a moment's notice, allowing it to adapt to drastically different conditions or mission needs. And it can be obviously a force multiplier with autonomy. So what we're really talking about here is the uncertain and unsafe nature of the edge environment. The example diagram that we've provided here is a pretty straightforward one. We have an unsuspecting warfighter. They're about to be ambushed, and they must react to that threat. And in order to maximize their ability to survive the encounter, the devices the warfighter carry should immediately recognize the change in state and adapt accordingly, which may result in automatically stopping some software services and starting others in order to immediately support the new needs of the warfighter. An easy example would be if I'm walking around trying to find a person of interest, I might have facial recognition software running that's pulling video off of a shoulder-mounted camera or something like that. And now I'm in a situation where I need to fight for my life. All that stuff goes away. And what I've done is I've turned on processing of audio data to allow me to determine where the gunshots are coming from, for example. So the architectural tactics that can be used to address this need, once again, fall upon modularity and monitoring of the environment. Now, I should be clear that in this case, we're not necessarily talking about autonomy. It can be an autonomous thing. Like I said, it can be a force multiplier if you do that. But the state triggering of whatever that state change could be manual, depending on the conditions that cause it. And so the key tactic that we're worried about is modularizing the capabilities, the various capabilities that are available on the device, so that services can easily be swapped at a moment's notice, including things such as having your services queued up, you can have them dormant, or even paused using platform orchestration tools, so that the system can immediately switch over upon receiving the trigger wherever it comes from. And this is really the first part where microservices become a key part of the solution space, as containerization of services and advanced configuration and orchestration is ideal for adapting for a changing set of needs. This also has significant overlap with the survivability tactics of assigning services to available hardware in a prioritized way. Different modes of operation may require different allocations of resources, and the platform should ideally be able to reallocate everything transparently to optimize resource usage at the moment of change. But depending on resources, there might be some level of inefficiency at the moment of change due to the need to get everything running because that's a priority, which is then slowly moved to the optimal distribution as the opportunities allow. Now, again, I can't necessarily talk about the specifics of experience that led us to identify adaptability as a key quality attribute in the edge environments. I do think it's worth mentioning that in the last several years, we encountered a number of frameworks that are designed for edge environments. The most notable one that you guys may have heard of before is the Robot Operating System, or ROS, which it's notable because it runs, and don't quote me on this because I'm not a ROS expert, but probably the majority of the major robotics projects, especially those used in events like the DARPA Grand Challenge. But of those frameworks, including ROS, my impression that I got was that adaptability from a moment-to-moment context change was a somewhat unique requirement that is perhaps underserved. Not to pick on ROS, again, it is certainly best in breed for automation of robotic platforms, but frameworks like it certainly respond, and it's important to recognize that frameworks certainly respond quickly to sensor input. But the robots, if you're going to field a robot using ROS, you're probably going to stack enough processing power and resources to do all the capabilities are needed and don't need to necessarily reconfigure services on the fly based on massive context changes. Mobile devices at the tactile edge typically also don't have that luxury. So I would encourage work in this space, either for humanitarian or warfighter missions, to make sure that the capability to adapt to major changes in the situation are handled. Okay, moving on. All right, so our fifth quality attribute is flexibility, and let's go ahead and define that. What we're saying here is that limited devices at the edge generally only support limited computing tasks, driving mission-specific assignment of equipment. Flexibility means the system can support multiple missions and switch between mission assignments as needed. Now, of course, flexibility is a closely related quality to adaptability, but it focuses more on the breadth of possible services provided by the mobile device rather than the speed at which it can switch. The scenario diagram that we're providing here provides a good example of this. A construction worker in a disaster area encounters someone in need of medical attention. While the call goes out, the mobile device that they're carrying can switch from construction-based support to medical guidance, assisting them in providing basic support. Similar situations may happen at the tactical edge when a warfighter receives new mission orders while out in the field and has to reconfigure the devices to support the new goals, such as turning on voice or facial recognition suites in order to find a person of interest. The tactics that we use to enable flexibility are pretty straightforward. We're pretty good at these. We're talking about taking advantage of general purpose computing to switch between computational capabilities, which is something that modern smartphones certainly do quite well, using user interface layers, modularity of applications, and library resources for services to interact with the platform in a standardized way. With that said, not all warfighters or even emergency responders are going to have a general purpose device like a smartphone while in an edge environment. Or if they do, it might not be particularly computationally powerful enough to make a real difference, especially in emergency situations. Therefore, the purpose-built devices that they are issued should support at least some level of flexibility in the tasks and missions that they support in order to allow the users to react to changing needs. Of course, as many of you, I'm sure, are familiar, most organizations are starting to roll out smartphone-based applications, but we do understand the limitations, right? They are a communication device, they're information device. With respect to what you might need to do in these environments, they may not be powerful enough in order to do what you want, so the need remains. Okay. All right. Let's get to that last one that Grace was excited by. So let's focus next on distributability, which we're defining as, given the limited capability of mobile devices, a system at the edge will be most capable if it takes advantage of nodes working together. Distributability means that a system can operate across multiple edge nodes in concert. And this is another quality attribute that really benefits significantly from the use of microservices. The idea here is that given the assumption that devices in the edge environment will have limited resources, you can realize increased capability by distributing computation across the devices that are available. The example scenario that we provided here shows a multi-stage process in which a drone is capturing video, which is then pre-processed on a larger node, such as a helicopter or some sort of UAV, which is then displayed in an augmented reality to an operator that is safely behind cover so that they can, despite the fact they don't have line of sight, they can still see the danger that's coming. This allows three nodes that provide a piece of the solution to collaborate and help keep the warfighter safe. Now, while there might be less call to use this kind of capability at the humanitarian edge, you can still imagine certain situations where combining computational power of devices during disaster recovery, for example, if we have a building that's half fallen and there's potential of rubble shifting, you could potentially shorten on-site analysis if you're able to combine your computational resources in order to analyze what you can see to provide guidance on how to safely dig for survivors. Architecturally, certainly we want to focus on modularity tactics to ensure that our different services can run in different places. But we also want to focus on the general messaging pipeline between nodes. Enabling arbitrary nodes to run arbitrary services requires careful orchestration of your message passing, which requires a use of distributed messaging architectures. As an example, a common one we've encountered many times now is something called 0MQ, which is an industry-leading message middleware system that is used in many places, such as by the Large Hadron Collider, where it collects terabytes of data every day. This approach naturally leans into the orchestration of microservices that I'm sure many of us are familiar with by platforms such as Kubernetes, where containers are started, stopped, reallocated, and connected as appropriate. Of course, there are several container orchestration engines out there as well. That particular issue of how those different options interplay is kind of outside of the scope of the talk, but it is an important consideration when it comes to distributability. I do have some thoughts on that if people want to ask questions, but the point is that it is clear that the ability to distribute computation across multiple limited resources, especially in edge operations, is very valuable. All right, bring on the questions.
So Mark, I want to be respectful of your time because I want you to get through all your slides, but there's a lot of traffic in the chat. Okay. And because this is a software architecture audience, of course, there are many questions related to trade-offs. Sure. So there is a question that I thought was very interesting, which is, to what degree is system complexity a factor? The reason for this question is, for example, if you add autonomy elements, that obviously increases the complexity of the system.
Yep.
And it is well known that if you add complexity, you're making a system more fragile, less resilient, which kind of is counter to a lot of the quality attributes you talked about. So to what degree is system complexity a factor in these types of systems?
I mean, there's no question it's a factor, especially when you start talking about distributing, not necessarily among different processors in a single node, but across multiple nodes, right? So what you have to do in order to compensate for that complexity is to make sure that your general purpose logic that drives the whole thing is pretty straightforward. Like, so something that we rely upon a lot is your asynchronous pub sub. And for the most part with stateless services, right? So whatever service you need to run, they process data and they put out data and they publish and they subscribe to whatever they need. And so with dedicated nodes that do the logic, like we're in combat state, or we're in evaluation state, or we're in special site exploitation state, whatever that state is, that kind of sets everybody. These are processing constraints, and then everybody else just continues to go off and do their job. And you can imagine doing those sorts of things either manually or autonomously. It's that careful mix of both where the logic lies, the level of complexity in that logic, and then how that message is distributed so that each individual service can do their task is the balance you want to drive. Because I certainly wouldn't want to have AI ML making all the decisions for all the services across 50 nodes kind of a thing. The distribution application becomes difficult, and especially when you're dealing with reliability issues with your network environment in these situations, that there becomes a lot of race conditions. So yeah, it's an acceptance of the reliability issues for your connectivity, acceptance of simple services, and then kind of encapsulating whatever complexity that you need to have for your state management into something that can be combined and worked out in a single unit, or at most a couple of small. Any other questions?
Go ahead,
Okay. All righty. So the last quality attribute that I'm going to touch on here is openness. We don't really have a diagram for, because it's more focused on the software construction side and integration rather than a specific edge challenge. In this case, we're going to define openness, and I'll just go ahead and read the slide so that the audio recording has the content. So given the challenges of the edge and the historical mix of software and devices which are provided to soldiers and first responders at the edge, we cannot expect that one vendor or organization will solve all these challenges. Openness means that the system must use well-defined, open, and well-supported interfaces and platforms so that any organization with an effective software or hardware solution can easily integrate their contribution within the system. And it's our experience that, especially in these edge environments, everybody comes to the table with one piece of the solution. Nobody has each challenge fully solved. So you can't just buy one device or one tool. As such, when it comes to constructing software for the tactical edge or the humanitarian edge, we're left with a situation where we need to enable easy integration of components. And using well-defined interfaces within the architecture becomes a critical feature of any architecture. We have direct experience with this, and while I can't really give, again, I hate to be doing this, but I can't give any details, but I will say that the ability to integrate in days or weeks on that kind of timescales versus requiring a timescale of weeks or months to integrate can move a project from being viable to non-viable. If your time scale slips out on that second order, more often than not, the project will be canceled. Or, in even the worst case, you can talk about something like the F-35, where, your project slips for year after year. It's costing extra billions or millions of dollars, and it's potentially even a worse outcome. So, looking at it from a software program management perspective is just as important as looking at it from a capability perspective, because if you can't build the thing you want to build, whether or not it was a good thing to build, the warfighters and or the first responders, they just aren't going to have it. So it's an important quality attribute that enables the construction of these systems. That is openness. Any questions on that one, or shall we finish up? So the last slide in this just kind of gives you a final scenario here. So having discussed all the quality attributes and how they relate, we're going to provide you a little bit more detail on a tactical edge scenario where different nodes are communicating different data types and performing different actions. Each of the quality attributes we've discussed come to play in architecting systems to support a scenario like this. Now, our warfighters currently, of course, as we know, have much of the capability that's described in this scenario. You have drones provide data feeds, relay nodes to higher headquarters, targeting from remote nodes provided to strike platforms, and advanced processing for soldiers on the ground that are in combat. But as you might expect, each of these capabilities are provided by purpose-built systems that cost millions of dollars and are a huge effort to interoperate. Our goal within the software community should therefore be to provide the next generation of devices with software architectures that are optimized for this environment, allowing our warfighters to field devices for less time and with more interoperation and with better optimization of the nodes that are available. Our hope here at the SCI is that webinars like this one will provide insight on how to do so that you, the community, can meet the needs of the first responders and the warfighters in the future. Okay. All right. Final section, let's wrap up with a few specific discussion points with respect to microservices in edge environments. So I've discussed all of the topics listed here, and this is kind of where we bring it all together. Microservices as an architectural element serve all these quality attribute needs that we've identified as priorities for operating in edge environments. Mature technologies such as Docker and Kubernetes allow us to perform the types of monitoring and reactivity that we need to be able to meet the reliability and survivability needs of the warfighter and the first responder, while also meeting our goals for adaptability and flexibility through statelessness and small footprint. We can start, restart, migrate, pause, and switch containers as necessary in an orchestrated way, allowing us to meet the goals that we're looking for. Similarly, the maturing of Docker and Kubernetes within the software community and similar technologies allows the general purpose applicability to most hardware platforms and software operating systems, making it easy to integrate with other systems as well as allocate services across different nodes. Finally, microservices are the ideal architectural component for capturing, processing, and reacting to sensor data as necessary. As we know, most major autonomy capabilities rely upon collections of orchestrated microservices, and applying those patterns to the devices at the edge, we can bring that capability forward, maximizing the use of resources that we have on hand. So in short, the ideal of scaling down, optimizing resources that you have in these challenging environments is best realized by the use of microservices. Okay. Moving on. All right. And so just to finish up, I have 2 more slides, and we're going to provide some examples to look at for reference. Here, I've listed a number of hardware and software devices that are typically leveraged in edge environments. I'm not going to read everything here, and I've mentioned several of the software elements such as Kubernetes and Docker, but the hardware list can potentially give you a sense for the options in the space if you're not familiar. If you do have questions about specific technologies, feel free to put them in the chat, and I'll give you my thoughts, but I will certainly be the first to say that I'm not familiar with everything on this slide, all the different options. Yeah. Okay. And finally, what we're trying to provide here is an example instantiation of those hardware and software technologies using the tactical edge scenario as a guide. As you can see, different nodes have different hardware resources, and more importantly, different missions that require different services. Some nodes, such as the warfighters in the upper left, may be under fire and have no time to look at their devices or manage what they're doing. So autonomy, survivability, and adaptability become key enablers there. Distributability above the nodes are seen in the drone comms to the other teams and the limited devices that are available, using reliability and flexibility solutions to adapt to the environment and the needs of the current mission. And making everything working together in any kind of reasonable timescale requires significant openness of the underlying architectures. And okay. And that's our presentation. And it looks like we have about 6 minutes, so we're right on schedule. Plenty of time for some final questions.
Thank you, Mark. Yes, that was really good. Lots of questions. So I'm going to try to pick themes here. But one of them has to do with this idea, and that we've talked about before, which is this idea of like local optimization versus global optimization.
Sure.
If you have a distributed system like the one you showed,
Yep.
where you have multiple nodes and multiple nodes are making their own decisions for survivability,
Sure.
and if you add in the autonomy piece in there, do you think you were ever going to run into situations where you have two of these nodes optimizing locally, but from a higher perspective, they have conflicting decisions? So, for example, the example that was brought up was friendly fire. Could there be a chance where we both optimize, but we get in a situation of friendly fire because we both optimize locally instead of globally?
So specifically to friendly fire, just to throw that out there, that is a very specific issue because our experience shows that the DoD is not in a place where they want to allow autonomous decisions to be making, actually doing fire for effect. You don't necessarily want to be pulling the trigger, shall we say. But it is absolutely true that, especially if you're optimizing for something like survivability, nodes have different priorities. And what I will say is because the assumption of operation in these environments presumes reliability challenges, especially with connectivity, there is a presumption that any node that you may be cooperating with may go away. And they may go away because you can't connect to them. They may go away because they've damaged or destroyed. And they may go away because they have something more important they need to do. And so if you start with that context, you understand that each node, therefore, must be able to adapt to the other nodes disappearing as best they can. Now, in some cases, that will cause missions to be no longer viable. And there is also a concept within the DoD about mission overriding necessarily, life critical decisions, right? So there are situations where the overriding mission that comes from higher headquarters or wherever it comes says this needs to happen, and if you need to sacrifice yourself or your devices to do it, that is a policy and doctrine decision that they can decide to make. But that gets back to the environment that you're in. Tactical edge devices should respect those decisions if they are asked to. Often, however, it is, in the most case, it really comes to the reliability challenge of not presuming another node that you're collaborating with will be out there and having some sort of default survivability behavior that will then allow you to adapt as best you can based on who you're talking to. And it's that external and internal monitoring that you need to rely upon to understand your context.
Okay, Mark. One last question before I hand it over to Shane. Thoughts on security as a quality attribute being critical in these scenarios?
Absolutely. That is obviously a huge question. As someone who has worked in this space and understanding the challenges that are there, I think the most important thing is to define your threat model, which is to say, where are the threats coming from, right? So can someone get your device physically and hack into that? If that's an issue, then you have to have a certain level of protection on the actual device itself. If someone can hack into your network, then you have to protect that network. If someone can, compromise your backend cloud services that you only sometimes connect to, then you have to have a more holistic solution, potentially some sort of zero trust architecture. This sort of thing really gets to understanding the sort of environment you're getting into. A lot of times what we've seen is that specific hardware is used, and that is used to define the boundary of trust. And so as long as you're within the boundary of trust, then we're only going to take a certain amount of additional caution. The reality of the situation is security has a cost, certainly a performance cost. And when you're in edge environments, every second can matter. So there is sometimes a trade-off between how much security I want to enable for your general purpose case versus how quickly I need this autonomous agent to be able to communicate with other nodes to be able to perform this task in this life critical situation. But absolutely agree, it is a quality attribute that is always one on the list that doesn't get as much service as it should. But since we understand it well enough, it should be part of that list you initially discuss when you are doing your design of your systems. And most important thing is to find that threat model so you can understand where you have to put in those interventions.
Thank you very much, Mark. This was really interesting. And Shane, back to you.
Yeah, Grace, Mark, thank you for the great discussion today and just sharing your expertise. We greatly appreciate that. We also thank everyone for spending the hour with us today. A reminder that today's event was archived. It'll be available once we close the stream. The archive will be up, and I'll check on about making the slides available as well. So if you found value in today's webcast, we ask you to hit the like button below and also share the archive with colleagues. And lastly, our next webcast will be on August 19th, which will be on risk management for the enterprise. And our speakers will be Matt Bukovic and Brett Tucker. Anybody that signed up for today's event will get emailed a registration link for that event as well. And lastly, any questions from today's event, feel free to send questions to info@sei.cmu.edu. Thanks, everyone. Have a great day.